All right, today we're going to look at the universal law of gravitation. When we look at this, we're going to do two things with it. You can probably do more, but we're going to only do two of them today. So the universal law of gravitation tells us that the force between any two objects is equal to big G. This is the universal gravitational constant, seen here as 6.67 times 10 to the negative 11 Newton meters squared over kilograms squared. I would recommend putting this in your calculator and storing it as G. So it's that universal gravitational constant times the mass of one of the objects times the mass of the other object divided by the distance between them squared. And when I say between them, I'm talking center to center distance, like this. All right, so we can use this equation to find the force of gravity between any two objects, between like two rocks, between planets, between you and a planet. Okay? And so this brings us to our first thing. So here on Earth, we talk about the force of gravity is just mg. But I'm telling you that the force of gravity is big G, big M, little m over r squared. So why the discrepancy? Well, when we use mg, the G, the 9.8, represents only a very narrow region near the surface of the Earth. This will tell me what the force of gravity is at any point, at larger distances. Okay, and so what we're really seeing when we see m times g is this right here has been lumped together to be g. And so, for instance, the acceleration of gravity on Earth is 9.8 meters per second squared. Right. So that's our first thing. We can find the acceleration of gravity on any planet based on the big G, the mass, and the radius of the planet squared. Now, the second thing we can do with this is we can start to talk about circular motion. So I'm taking the example here of Jupiter and one of its large Galilean moons, Ganymede, which has a nice circular orbit. That's why we're going to use it here. And it's going to revolve around Jupiter. And what our goal is here is just based on the separation distance I observe, which is 1.07 times 10 to the 9th meters, and the period, the time it takes to go around one time, 7.15 days, we can go ahead and calculate the mass of Jupiter. That's pretty cool. We don't have to actually go there and measure its density, because how else would you measure a planet's mass? So this is one nice way we can do it. So this is circular motion, so that means I will be summing up the forces, and it is circular motion, so the sum of the forces in the radial direction is MAC. There is only one force, and it is the gravitational force, and it is pointing in the same direction as AC, radially inward, which is my positive direction. So this will equal MAC, and I'm going to make that substitution, V squared over R. Now again, we're going to have to make another substitution because this is circular, uniform circular motion, I should say. V is going to be 2 pi r, the circumference, divided by the time it takes to go around that circumference, which is the period. And so we'll be making some substitutions here. So f of g is going to be big G, big M. That will be my mass of Jupiter, times the mass of Ganymede divided by the distance center to center squared is equal to the mass of Ganymede times v squared. So I have 4 pi squared r squared over t squared. And I do have this r on the bottom here. Now what you do notice is we don't actually need to know the mass of Ganymede to find the mass of Jupiter. Similarly, we didn't need to know the mass of the moon to find the mass of the Earth using this same thing. But in order to find the mass of the moon, we have to have something that orbits it. Without that, we're simply estimating. Okay. So here we go. We're doing more estimating than we are here. So I'm going to go ahead and solve for big M. So I'm going to multiply this r squared over. That makes this r to the 4th. And I got an r in the bottom, so that brings me down to 3, r cubed. Divide the G over, and so I have the mass of Jupiter is equal to 4 pi squared r cubed, that's a center to center distance, divided by period squared. Now later on, we're going to use this relationship of r cubed over period squared as being constant for things orbiting another object. But for now, we're just going to use it by plugging in our radius in meters and our period in, we're going to want to use seconds because we're using newtons in this. Okay. Oh, there's the G down there too. Almost forgot. And we're going to plug in that G, that period in seconds, the radius, and find the mass of Jupiter. And it comes out to be 1.9 times 10 to the 27th kilograms. Now I want to show you one more cool thing we can do with this. Now, when we look at other stars far away, we look for exoplanets. And one way we can do that is when we're looking at that that star, that exoplanet might be orbiting in such a way that it goes in front of our star. And so when that planet goes in front, a small portion of that star is blocked. Okay? And so it dims ever so slightly. And we can look, how often does it dim, and essentially calculate a period. Okay? Now, from that period of dimming, I can't tell how far away it is or how close it is. Okay? But from the light signature of that star, based on its temperature, essentially, I can calculate roughly its mass. And then using the mass of that star and the period, okay, I can calculate how far out that planet is. Okay? And based on how far out that planet is and the amount of dimming, I can then calculate the size of the planet. So you can imagine that if I had a planet like this and it was close in, it would maybe make a big dimming effect versus if it was really far out. Okay? It's going to only cover a very small portion. Okay? So that is how this works. Cool.